Welcome back to Meteorology 1010. This is Lecture 4, corresponding to Chapter 4 in your book, Humidity, Condensation, and Clouds. In the last chapter we talked about temperature. And after you get done with temperature, the next thing to concern yourself with is humidity, or water vapor, how much water vapor is in the atmosphere. So first we'll go through the circulation of water through the atmosphere, then talk in detail about evaporation, condensation, and the concept of saturation and how all that plays into humidity, and then a brief look at dew, frost, and fog, and clouds. So the hydrologic cycle, not the hydraulic cycle, but the hydrologic cycle, the movement of water through the atmosphere and through the ground and the oceans and the lakes and the rivers. This is the type of illustration you've probably seen very likely since grade school. Pretty straightforward stuff. Evaporation of water into water vapor, and then condensation into clouds, then precipitation in the form of snow and rain, and then runoff and glaciers and groundwater and lakes. What's interesting about the hydrologic cycle, if you take all the water vapor that is in the atmosphere and you were able to precipitate it out, it would cover the globe in about an inch of water. And if you precipitated it out in the form of rain and snow as we know it, it would take about a week worth of global rainfall for that to occur.
Water is essential to life. All living organisms are composed of water. But about 97% of water is locked in the oceans. The atmosphere holds much less than the oceans, only about 13,000 cubic kilometers of water per year. So how do we get drinkable water? To understand this, we need to learn how water cycles from the ocean to the atmosphere, to the land, and then back to the ocean. Let's start with the sun, as it drives the water cycle by heating water in the ocean, soil, streams, rivers, and lakes, causing it to evaporate into the atmosphere as water vapor. In fact, evaporation returns about 85% of the water vapor to the atmosphere. In addition to evaporation, there is another way water can enter the atmosphere. Plants lose a significant amount of water vapor through their leaves during the process of transpiration. Evaporation and transpiration together is called evapotranspiration. After water vapor enters the atmosphere by evaporation and transpiration, it cools and condenses to droplets, forming our clouds. As clouds form, wind is continuously moving these air masses over the land. In fact, wind moves about 40,000 cubic kilometers of water in air masses over the land. But what happens when the clouds can't hold moisture any longer? Water is released from the clouds in the form of precipitation, which can be rain, sleet, snow, or hail. A total of about 496,000 cubic kilometers of precipitation falls to the land and ocean. So where does water go once it falls on the land? It may re-enter the atmosphere by evaporation, or it may infiltrate and percolate, which means seep into the soil to become groundwater, water in soil, and aquifers. Aquifers are permeable rock that holds water. Groundwater is necessary for all living organisms and also recharges all bodies of water. What if precipitation happens faster than water can enter the ground? Water then remains on the surface as runoff and flows into streams, rivers, lakes, and eventually the ocean, completing the cycle. The hydrologic cycle continues to move about 100 million billion gallons of water a year. Without this process, life on Earth would be impossible.
All right, to the meat of it, evaporation, condensation, and saturation. Evaporation is a change in state from liquid to vapor. It is, as we have learned with our study of latent heat, it is a cooling process. Evaporation of liquid water into water vapor is a cooling process. Now remember, clouds are made up of liquid water droplets. Water vapor, or I should say water droplets that evaporate into water vapor, become invisible. Water vapor is not visible. Condensation is a change in state from vapor to liquid, and condensation, going from vapor to a liquid, that is a heating process. It literally releases sensible heat. Evaporation absorbs heat, so it is a cooling process. Condensation releases heat. It is a heating process. Now, at any given time over any surface of water, both condensation and evaporation are occurring at the same time. Over a surface, there are water molecules that are leaving the liquid state and becoming vaporous, and there are vapor molecules that are re-entering the liquid state. So over any given surface of water, condensation and evaporation occur at the same time. And that's what we see under A in your illustration. Now again, our little Mickey Mouse friends there, the red oxygen with the two hydrogens, H2O, those are our liquid water droplets, or I should say our water molecules in the liquid state, and the ones flying around with the swooshes behind them are the water vapor molecules in the vapor state. So if you enclose the surface, as we see we have done in B, if you enclose that surface, eventually the number of molecules evaporating and condensing will come into equilibrium. So what that tells us is if you enclose that space over that glass of water, you put a lid on it, then eventually and fairly quickly the number of molecules that are leaving the surface of the liquid water and becoming vaporous will come into equilibrium or be equal to the number of molecules that are going out of the vapor state into the liquid. And when that occurs, when there's an equal number evaporating and an equal number condensing, then the air is said to be saturated. It is at 100% relative humidity. That parcel of air, that slice of air, that chunk of air cannot hold any more water vapor. And that is why if you put more water vapor into it, one more molecule goes into vapor, then one molecule has to come out of vapor and become liquid. So that is saturated air. For every molecule that evaporates, one must condense with no net loss of liquid or vapor molecules. Condensation nuclei. These are the little nucleus that condensation occurs on. So what is a condensation nuclei? Well, tiny particles upon whose surfaces condensation of water vapor begins in the atmosphere. So condensation does not necessarily occur spontaneously in the atmosphere. In the previous example, the water vapor was condensing onto an existing water body, and so the actual water molecules of the liquid acted as the condensation nuclei. In the atmosphere, just out in the free atmosphere, water vapor molecules that are zipping around, they don't spontaneously condense. They need something to condense to, and what they condense to are tiny particles in the atmosphere known as condensation nuclei. What is the impact of temperature and wind on evaporation? Well, wind and warmer temperatures both enhance evaporation. So this is a picture of condensation, but if we consider evaporation, as wind blows over any water surface, whether it's drops of sweat on your skin, or the puddle on the ground after rainfall, or a lake or a river or an ocean, wind will enhance evaporation. It will pull more water molecules not only off the surface, but move them away so the air never becomes saturated. And warmer temperatures enhance evaporation, and that's intuitive. You heat up a pan of water and it evaporates away. A puddle of water on the ground on a hot summer day will evaporate very quickly, whereas a puddle of ground on a cool fall day, that puddle may not ever evaporate. It may just sit there for days. So wind and warmer temperatures both enhance evaporation. So what is the temperature impact on condensation? So what happens in the atmosphere? If you look at our A and our B in our illustration, is notice the swooshes on the water vapor molecules on the left. The swooshes are very long, indicating that they're moving very quickly, and fast molecular motion means warmer temperatures. So when the temperatures are warm and our molecules are moving quickly, those water vapor molecules tend to bounce off the condensation nuclei. Whereas in colder air, the swooshes are very small, the water vapor molecules are moving very slowly. In colder air, those water vapor molecules tend to stick to the nuclei. So condensation occurs more easily in cooler air. As a matter of fact, condensation occurs primarily when air is cooled. Air molecules in warm air are moving faster and tend to bounce off condensation nuclei, while slower moving molecules in cooler air tend to stick and condense onto the nuclei.
As the temperature inside the jar lowers and approaches the dew point, the relative humidity increases. The closer the air temperature is to the dew point, the greater the likelihood that water vapor molecules will stick to tiny condensation nuclei. When the air reaches saturation, a significant number of water vapor molecules are able to condense onto the nuclei, forming a visible cloud. When the temperature inside the jar rises, the relative humidity lowers. Water vapor molecules quickly evaporate from the liquid droplets, and the cloud disappears.
So what is humidity actually? Humidity refers to one of any number of ways to specify the amount of water vapor in the air. Now, on this slide and in your book, we discuss several types of humidity, each derived by a different method. In the end, however, the humidity we'll mainly be talking about is humidity as measured by relative humidity and humidity as measured by the dew point. So just briefly, we'll go through these others. There's absolute humidity, specific humidity, the mixing ratio, and vapor pressure. Absolute humidity is the mass of water vapor in a given volume of air. So how much actual vapor is in a given volume of air. Specific humidity, the mass of water vapor in the parcel compared to the total mass of the air in the parcel, including water vapor. Just a little bit different. And then the mixing ratio is the mass of water vapor in a parcel compared to the mass of the remaining dry air, splitting the two and making a ratio. That's the mixing ratio. Vapor pressure. Vapor pressure is something we'll have to get a handle on, though. Vapor pressure is something you'll see again, and you'll probably see on assessments as well. Vapor pressure is the total pressure the water vapor molecules exert inside an air parcel. Now, remember, when we talk about a parcel of air, we're talking about a human construct, a theoretical parcel. There are no parcels of air in the atmosphere. We're talking about an enclosed, kind of think of it maybe as a balloon of air without the latex on the outside. It's just a parcel of air. All vapor molecules, whether they are oxygen, nitrogen, methane or nitrous, or water vapor or CO2, all vapor molecules exert pressure. We've already talked about air pressure. The amount of pressure standing at the surface is the mass of all the air molecules above us, whether it's oxygen, nitrogen, all of them all added together. That's the air pressure. So the total pressure that just the water vapor molecules exert inside a parcel of air is known as the vapor pressure. So the vapor pressure, also called the partial pressure, is the partial pressure that water vapor molecules exert in a given parcel of air. Now, we've talked about the air parcel before. It is an imaginary structure, kind of a balloon of air, and everything within that parcel constitutes the atmosphere in that parcel. So here you have an example. We have oxygen, of course, diatomic, two molecules together. That's in the red. We have the nitrogen, diatomic, two molecules together. That's going to be in the green. And then there you see Mickey Mouse flying around in this air parcel as well. Our water vapor, our H2O, two molecules of hydrogen, one of oxygen. I count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So let's just say 10. And so the partial pressure or the vapor pressure in this air parcel is going to be 10. 10 what? Well, we'll call it 10 millibars in this case. Whereas if we're going to count the partial pressure of oxygen, I see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. The partial pressure of oxygen is 11 millibars in this case. And then what is the partial pressure of nitrogen? We'll count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Also 11 molecules of nitrogen, so 11 millibars, for lack of a better term. So we have 10 millibars partial pressure of vapor. Vapor pressure is 10 millibars. 11 millibars partial pressure of oxygen, and 11 millibars partial pressure of nitrogen. So our next concept is not vapor pressure, but saturation vapor pressure. And saturation vapor pressure is not a measure of the amount of vapor, water vapor, in an air parcel, but saturation vapor pressure is the pressure that water vapor would exert if the air were saturated at a given temperature. So A parcel of air may or may not be saturated. If the parcel of air is saturated, it's holding as much water as it possibly can, then the partial pressure that that vapor is exerting is the saturation vapor pressure, the pressure that water vapor would exert if air were saturated at a given temperature. Let's take a different parcel of air, one that is not saturated. The relative humidity is below 100%. The saturation vapor pressure, if it's at the same temperature, would be the same because it would require the same amount of water vapor to reach saturation or 100% relative humidity. So the saturation vapor pressure is the pressure that water vapor would exert if that air were saturated at a given temperature. So saturation vapor pressure depends on air temperature. And essentially, the warmer their air is, the more it can hold, more water vapor it can hold. So the higher the saturation vapor pressure will be. And the cooler the air is, the less water vapor it can physically hold, and the lower the saturation vapor pressure is in that parcel of air. Higher temperature, higher saturation vapor pressure. Lower temperature, lower saturation vapor pressure. If you increase the temperature, you are increasing the average energy of the molecules. They're moving faster. Higher temperature means more of them are likely to have enough energy to escape from the surface of liquid water. The increase in temperature increases the number of molecules of H2O in the air and thusly increasing the saturation vapor pressure. At higher temperatures, it takes more water to saturate the air. Higher temperatures equals higher saturation vapor pressure. So what is the relative humidity? Well, the relative humidity is the ratio of the amount of water actually in the air to the maximum amount of water vapor required for saturation at a particular temperature. So we call it relative humidity, which means it has to be relative to something. Well, it's relative to what? That's right, temperature. Relative humidity is the ratio of the amount of water vapor actually in the air to the maximum amount of water vapor required for saturation relative to the temperature. So, to say it another way, and we're going to say it two different ways, which is going to make it easier to do the math, relative humidity equals the water vapor content over the water vapor capacity. What do I mean by that? Water vapor content. The relative humidity equals water vapor content over water vapor capacity. The content is the amount of water vapor that's actually there. Have that parcel of air in front of you one more time. How many water vapor molecules are in that parcel? That is the content. It is actually there. It can be measured. You can count the molecules. If you could count the molecules, you would be able to count those molecules. Whereas the water vapor capacity is the maximum amount of water vapor required for saturation at a particular temperature. Remember, as the temperature goes up, the maximum amount of water vapor required for saturation also goes up because warmer air holds more water vapor. So relative humidity is water vapor content over water vapor capacity, or content over capacity. And said another way, then relative humidity is vapor pressure over saturation vapor pressure. Relative humidity is vapor pressure over saturation vapor pressure. Relative humidity tells us how close the air is to being saturated, not how much vapor there is in the air. What that means is very, very cold air has very, very few water vapor molecules because it is cold. It could still have a very high relative humidity, but the number of molecules may still be very low, as opposed to Central Florida air in the summertime, where we have a tremendous amount of water vapor in the air because the temperature is so much warmer. But relative humidity does not tell us how much vapor is in the air. It tells us how close that air is to being saturated. Air at 20% relative humidity is very, very far away from being saturated, whereas air at 98% relative humidity is close to being saturated. How do you change the relative humidity? Well, you have to change the content or the capacity. How do you change the content? Well, you physically put more vapor in or physically take more vapor out. How do you change the capacity? Well, capacity is relative to temperature. So a change in temperature can change the relative humidity. A change in relative humidity occurs when there is a change in the air's water vapor content or vapor pressure, or there's a change in the air's temperature, the saturation vapor pressure. So this is where we illustrate that. So 4 different vessels with water vapor in them. So these are going to be your parcels of air. There's a little water at the bottom, so water's evaporating and condensing. But you can see at the top, A, we have two different vessels, two different parcels of air, both at 20 degrees Celsius. So that means their saturation vapor pressure is the same. Their capacity to hold water vapor is the same. So 20 degrees Celsius. So how would you increase the relative humidity in that parcel in A? Well, you'd have to increase the water vapor content. You can see over on the left side, you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 water vapor molecules flying around. And then on the right-hand side, maybe you have 20 water vapor molecules flying around. The little swooshes are the same length, meaning they're moving the same speed because of the same temperature. But at the same temperature, in order to increase relative humidity, you have to increase the content. Down in B, we have two vessels with the same number of water vapor molecules, but notice what's different about the swooshes. On the left, they're slow because they're still at 20 degrees Celsius. But on the right, they're very long. They're moving much more quickly. They're at 30 degrees Celsius. And by raising the temperature, you decrease the relative humidity. The content stays the same, but the parcel's capacity to hold air increases significantly. At a higher temperature, the parcel's capacity to hold air increases significantly. So the relative humidity goes down. At the same temperature, an increase in water vapor content of the air increases the relative humidity as the air approaches saturation, as seen in A. In B, if you hold water vapor content constant and increase the temperature, causing a decrease in relative humidity as the air moves further away from being saturated, and a decrease in temperature causes an increase in relative humidity as the air moves closer to being saturated. All right, so because of this interesting combination of temperature and relative humidity, where as the temperature goes up, the relative humidity goes down as long as you've not changed the vapor content of the air, and as the temperature goes down, the relative humidity goes up as long as you've not changed the vapor content of the air. You have an interesting sort of inversion between temperature and relative humidity. Let's start at midnight, fairly close together. As it cools off, the red line gets lower and lower and lower. The relative humidity gets higher and higher and higher, meaning the air early in the morning at the coolest part of the day is closest to saturation, or 100% relative humidity. That's when your fog forms. That's when your dew forms on the grass. If the air can get to 100% relative humidity because of the temperature drop, then fog will form, or dew will form on the grass. As the day progresses, closer and closer to noon, as the temperature increases, that relative humidity gets lower. Now, the amount of vapor in the air is the same. That's the contingency here. The amount of air, water vapor in the air has not changed. So you still feel horribly humid at 5 o'clock in the afternoon, but the relative humidity has gone down only because, again, that temperature has gone up. So what is the dew point? Oftentimes when you see media presentations of the weather, we'll talk about temperature and dew point. The dew point is also a temperature. The temperature, obviously, 72 degrees Fahrenheit, 14 degrees Celsius, whatever it happens to be. But the dew point is also measured in temperature. The dew point temperature is the temperature to which air would have to be cooled with no change in pressure or moisture content, meaning you're not going to change the amount of content in the air. All you're going to change is the temperature. The dew point is the temperature to which air would have to be cooled for saturation to occur. So when air is cooled far enough, then saturation occurs and condensation results. That's how you get the dew on the grass in the morning, and why we call this the dew point. Adding water vapor to the air increases the dew point, and removing water vapor from the air lowers the dew point. The more vapor there is, the more water vapor there is in a parcel of air, the higher the dew point, the closer it is to being saturated. The more moisture you put in there, the higher the dew point. If you remove water vapor from a parcel of air, again, you have your imaginary parcel of air. If I take water vapor out of it, that lowers the dew point. Now, a typical dew point in Central Florida in August in the afternoon may be 72 degrees, where a typical dew point in Central Florida in January may be 50 degrees. So what that means is in January, in an afternoon, if you were lower the air temperature down to 50 degrees, the air at that temperature would be saturated and condensation would begin to occur. Same thing happens in in August at 72 degrees. If you lower the temperature to 72 degrees, then condensation occurs because saturation is reached. Think about your cold beverage, whether it's your water bottle or your can of something, sitting out by the pool on an August afternoon. What happens on the outside of the can, or what happens on the outside of the water bottle? Well, of course, water droplets begin to form. Dew gathers on those cans and on those water bottles. Well, why? Because the cold can or the cold water bottle has cooled the air around it to the dew point, and condensation has begun to occur. The difference between air temperature and the dew point temperature indicates whether the relative humidity is high or low, with a greater dew point depression. So the difference between the air temperature and the dew point temperature is the dew point depression, and a greater dew point depression indicating lower relative humidity and drier air. So if your dew point is 50, but your air temperature is 80, that's a very dry air, as opposed to if your dew point was 78 and your air temperature was 80, that'd be very, very humid air, high humidity, high relative humidity. And smaller dew point depressions like the one I just described indicate higher relative humidity and more humid air. And we will discuss the wet bulb temperature, the lowest temperature that air can be reached by evaporating water into it, in class.
As the temperature inside the jar approaches the dew point, the air is approaching saturation and the relative humidity of the air increases. When the air temperature reaches the dew point, the air is saturated and the relative humidity is 100%. As the temperature moves away from the dew point, the relative humidity lowers as the air moves farther away from being saturated.
So, dew point distribution. This should be no shock to anybody. Where are the dew points the highest? Well, of course, around the Gulf of Mexico and the southeast coastline, including Florida of the United States. Where are they driest? Out on the Colorado Plateau at high elevations, where in the wintertime the dew point may be as low as 10, and the summertime around 40. And can dew points be a negative temperature? Absolutely. Dew points can be below zero. And then you don't get dew forming. What do you get? You get frost forming. So it's not the heat, it's the humidity, right? Well, that goes back to temperature, humidity, and human comfort. The main source of cooling for the human body is sweat. The evaporation of sweat is a cooling process. It cools the body. When the water vapor content of the air is very high, sweat will not readily evaporate, and natural cooling processes are not effective. So the heat index is a National Weather Service index that combines temperature and water vapor content to produce an apparent temperature, that apparent temperature being the heat index. So there's a number of ways that you can measure humidity. The sling psychrometer is an instrument that has one normal thermometer, and then right next to it a wet bulb thermometer, which is nothing more than a thermometer with a little sock around the bulb. You get that sock wet and you spin it around. That's why they call it a sling psychrometer. And you get an accurate temperature reading, and then right around the wet bulb where that sock evaporates, well, evaporation is what? It's a cooling process. So that bulb shows a different temperature, and that sling psychrometer with those two different temperatures will give you an idea of the humidity. Other hygrometers, that is, hair hygrometer, electrical, infrared, dew point hygrometer, all use different methods. Electrical, well, water is a conductor of electricity, so the higher the humidity, the more conductive the air, and that's how electrical hygrometers work. Hair hygrometer is pretty darn simple. What happens to your hair when it gets humid? Curls up, right? So they take a horsehair. Of course, this is old school. They take a horsehair, stretch it between two very sensitive instruments, and as the humidity goes up, the horsehair literally shrinks or tries to curl, and that's how they measure the humidity. All right, let's talk about the weight of air. So, show of hands. How many people think that humid air is more heavy than dry air? Well, maybe the first time in your life, but this will be a time when you're actually wrong on that one. Very interesting. Humid air is lighter than dry air, as it says in 50-point type at the bottom. And why is that? The amount of water vapor in a parcel of air determines the weight or the mass of that parcel. Because when water vapor content increases, the water vapor has to replace some other gases. Remember, water vapor is a variable gas. So if you increase the amount of water vapor in the air, you're going to replace the other gases in that air parcel. And mostly, because air is mostly oxygen and nitrogen, what are you going to replace? Well, if you increase the vapor in a parcel with a bunch of H2O, you're going to replace that oxygen and nitrogen. And water vapor, or H2O, is a relatively light gas when compared to oxygen, O2, and nitrogen, N2. I mentioned this before. Oxygen and nitrogen are diatomic. There's always two of them floating around in the atmosphere, not one. Oxygen has an atomic weight of 8, while nitrogen has an atomic weight of 7, or atomic mass. Since both of these elements are diatomic in the troposphere, O2 and N2, the atomic mass of O2, oxygen, is 16, and the atomic mass of nitrogen is 14. Well, water vapor is lower. Compared one oxygen atom and two hydrogen atoms, hydrogen is the lightest element with an atomic mass of 1, oxygen has an atomic mass of 8, so water vapor has an atomic mass of 10, significantly lighter than oxygen or nitrogen. So humid air is actually lighter. Humid air will want to rise. We know that warm air rises, well, humid air rises as well. So what happens if you have a whole bunch of warm and humid air? Well, it all wants to rise. At 10 atomic units, water vapor is lighter than diatomic oxygen and nitrogen. Thus, at a constant temperature, the more water vapor that displaces other gases, the lighter, less mass, the air will become. And humid air is lighter than dry air. How about density? Air density will vary as temperature and water vapor content varies. Density is mass divided by volume. Again, rho equals mass divided by volume. Density equals mass divided by volume. As mass decreases, water vapor content increases. Again, more water vapor, the mass goes down, then density decreases. So more water vapor, less dense, what does that mean it's going to do? It's going to float, right? More water vapor means the air is less dense. So humid air is less dense. When the temperature increases, the higher molecular motion results in an expansion of volume. Higher temperatures create more volume, and air is less dense. So both humid air is less dense and warm air is less dense. When a parcel of air is less dense than the surrounding air, it is buoyant. It tends to rise. If a parcel is more dense than the surrounding air, it's not buoyant. It tends to sink. And Mr. Archimedes explained that to us. So once again, just to reiterate, as water vapor content increases, density decreases. And as temperature increases, density decreases. So both more humidity and more temperature, more humid air and warmer air, both of them tend to be lighter than the air around them and tend to rise. So how can you change the density of a parcel of air? How can you make an air more buoyant or less buoyant? You can add or subtract water vapor, or you can heat or cool the parcel. Now, when do we heat parcels of air in Central Florida in the summertime? Right there at the surface. That's right, every afternoon as the day warms up, not only are those parcels humid, but they get hotter and they tend to rise. Good indication of why our summer afternoons are so active. So, this slide can tell you a lot about what happens with the weather. As the air cools, the temperature approaches the dew point temperature and relative humidity increases. When the air temperature reaches the dew point temperature, then the air is saturated and the relative humidity is 100%. Continued cooling causes water vapor to condense into liquid water as the colder air cannot hold as much water vapor. In the atmosphere, condensation of water vapor results in clouds, and at the surface, condensation results in dew, frost, haze, or fog. So why do I say that's important? Well, take our summer afternoon and a very humid parcel of air at the surface. As it heats up and heats up, it becomes less and less dense. As that parcel of air begins to rise in the atmosphere, what does it do automatically? As you go up in the atmosphere, what happens to the temperature? Well, the temperature begins to go down. So a parcel of air rising in the atmosphere automatically, as it goes up, begins to cool. Ultimately, it will cool until it reaches its dew point. When it reaches its dew point, that parcel is said to be saturated with a relative humidity of 100%. Continued lift of that parcel, or continued cooling, will cause the water vapor to condense into liquid water, as the colder air cannot hold as much water vapor, and that liquid water in the atmosphere is known as clouds. Now, if cooling occurs at the surface, as it does every night, then you get dew early in the morning, or frost if it cools far enough, or haze, or even fog. Fog is nothing more than a cloud in contact with the ground. Dew, frost, haze, and fog. And what is the difference? Dew is water that has condensed onto objects on the ground when the temperature of the object's surface has fallen below the dew point of the surface air. So you park your car in the yard, someone leaves their bike in the yard, whatever it happens to be, particularly metal things. Metal tends to cool very quickly. Remember, the thermal conductivity of metal is very high. So late at night, getting cooler and cooler, the windshield of your car, the hood of your car, the seat of your bike, all those things, they cool. And as they cool, if they cool to or below the dew point, well, the air around them cools as well. That air becomes saturated at 100% relative humidity, and condensation occurs, and that's where the dew comes from. Frost forms when the dew point temperature is at or below freezing. Call that the frost point. And the air cools below the frost point, allowing the deposition of water vapor directly into ice. So vapor doesn't turn to dew and then freeze. That would just be frozen dew. The vapor is deposited directly into ice. That's known as deposition. So you sort of, you completely get rid of condensation. You go directly from vapor to ice. Now, haze forms in the atmosphere as the relative humidity climbs to about 75%. At about 75%, water vapor begins to condense onto those condensation nuclei. But the condensation nuclei, the size of those wet particles, not quite big enough to scatter, to be seen, but they are big enough to scatter visible light. So as that visible light is scattered, it makes the atmosphere appear hazy. Fog forms when relative humidity approaches 100%, causing the water droplets to grow large enough to be seen by the naked eye. Again, fog is a cloud on the ground. A couple of different types of fog, all described in your book: radiation fog, advection fog, upslope fog, valley fog, and evaporation fog. So we're going to go quickly through the types of fog. Again, this is described in your book. Typical radiation fog: heat radiating away from the surface at night, cools the bottom of the air until it reaches saturation. Fog forms first at the surface, thickening as cooling continues. And so as you can see, further radiation and further thickening of the cool air at the surface, that fog gets thicker or deeper. Now, in the morning, when the sun comes up, the exact opposite happens. The sun's rays penetrate through the fog, slowly warming up the ground. As the ground begins to warm up, the air at the surface, right at the ground surface, warms up above the dew point. As it warms up above the dew point, that fog evaporates into vapor, and the fog lifts, and that's how fog burns off or lifts. Other types of fog: advection. Advection is the horizontal movement, or wind. Warmer, moister air moves over a colder surface, and its temperature drops, and fog forms, such as slightly warmer and slightly moister air moves literally through the Golden Gate into San Francisco and Oakland Bay. The water there is much colder, and so it cools that warmer air a little bit, and fog forms, and that's how the fog rolls in. And that can happen here in Central Florida as well with advection fog or sea fog. The Gulf Stream is warmer, and so the air over it's warmer and more humid. As it moves toward the shore over the shelf waters that are cooler, that fog can form, and it can move right on shore. Advection fog. Then there's upslope fog. As air rises with terrain, it cools and condensation occurs. There's also downslope fog, as cool air drains by gravity down into a valley. Now think about the mountains along the East Coast, the Smoky Mountains. So are they smoky all the time, or are they foggy all the time? Well, actually, they're foggy all the time. And that's fog because of the close proximity to the Atlantic Ocean, but higher elevation. So it's fairly humid air in a higher elevation that's cool enough to produce that day-long fog. Makes the mountains look smoky. And then evaporation fog. As rain falls to the atmosphere, it evaporates. Evaporation is a cooling process that leads to saturation, and fog can form when light rain happens. And you can remember some very, very gray days with light rain all day long. That's very, very chilly. Foggy periods develop. That's precipitation or evaporation fog, sometimes called mixing fog. And here is the distribution of the types of fog and the number of days that we have fog across the United States. And I just want to point out in western parts of North Carolina and Virginia and a good bit of West Virginia where the Smoky Mountains are, you can see they have a high number of days of fog. We have advection and radiation fog across the southeast coastline and across the northeast coastline and the northwest coastline where we have a close proximity to moist air. Upslope fog on the front range of the Rockies as we go from the plains right on up to those higher elevations, and then radiation fog in the high desert where temperatures drop very quickly at night. Cloud classifications. Now, we could do a whole class, a whole semester on cloud classifications. What I can tell you up front is we need to know the difference between stratus clouds and cumulus clouds. Stratus clouds are flat, stratified, layered clouds. Like the stratosphere, it's layered, it's stratified. So stratus clouds are flat. They tend to produce light precipitation, showery precipitation, and then cumulus clouds. And cumulus clouds grow into cumulonimbus clouds, and cumulonimbus clouds are our towering cumulus clouds that produce heavy showers, heavy rain, and lightning. Also, I want you to know that high clouds are cirrus clouds. Those clouds are completely made of ice. They're known as being glaciated. They're high enough in the atmosphere that the high clouds, the high cirrus clouds, are all little itty-bitty ice crystals. And so are the condensation trails you see behind airplanes. Those are ice crystals that have formed in the wake of the jets. Here's a pretty good illustration of different clouds. And again, look to the left on the bottom. You get stratus. They look like pancakes stacked up on top of each other. Whole sheets of air have been lifted to make these flat stratified clouds. If they stack up thick enough, you get nimbostratus, which is a cloud producing precipitation. Nimbo means that it's producing precipitation. You get that steady light precipitation, whereas your cumulus clouds go from white, fluffy, happy, smiley face clouds to big towering cumulonimbus clouds that produce heavy showers and lightning. In between, you have altocumulus at mid-levels, and then also altostratus. The altocumulus are those little, they refer to cellular clouds, little kind of like puffs that are all gathered together. Altostratus is when it's just kind of a hazy day and the sun is dimly visible. And then you get the cirrostratus, which you can't see at all except around the sun, and that produces that halo around the sun. That's in the high levels. So if you ever see a halo around the sun, that's just cirrostratus clouds. Also a halo around the moon, guess what? It doesn't mean anything, no vampires. It just means there's cirrostratus clouds. And the white light either emanating or emitted from the sun is bent, creating that halo. Or in the case of the reflected white light of the moon, it's being bent, creating the halo. And you also have those cirrocumulus, very, very small upper-level clouds, and cirrus clouds, I should say, right there in the middle. And those cirrus clouds are sometimes called mare's tails because they look like the tail of a horse. A female horse, a mare, at any rate. And all those high clouds, again, all ice. Here are some common terms identifying lots of other clouds. And if we had lots of extra days, we'd go out outside and look at the clouds around Central Florida. But I can tell you, you're welcome to read through these. And we may talk about some of these. Lenticular clouds are particularly interesting. Mammantas always indicate very intense weather. So we'll talk about some of those and show you a couple of shots. Here are those lenticular clouds. They typically form over mountains or on the lee side of mountains. The wind blows in from, in this case, the left or the west. It blows up and over the mountains, and the upward motion creates enough cooling to get some condensation in those lens-like clouds. Interestingly enough, those clouds will then blow downstream, and if they're very isolated at great distances, they do look like UFOs, and many of the Western UFO sightings are probably lenticular clouds. They look very peaceful and very tranquil, but the upward motion, and the downward motion of those clouds is actually very violent, and where you have that type of motion in the atmosphere without the clouds, they refer to that as clear air turbulence and very dangerous for airplanes. There's your pileus, kind of a little beanie cap on top of developing cumulus clouds. And there are your Mammantas. And the Mammantas hang low. They're the only clouds that develop from downward motion in the atmosphere. And they always have this ugly look to them, this orange look. Well, it's not because of the cloud itself. Typically, strong thunderstorms develop in the late afternoon when the sun is setting in the west. And so as the sun is setting, you have more reds as the visible light of the sun is scattered and leaving more of those reds, and so you get those Mammantas clouds that are illuminated red and look very, very scary. But whenever you have those bag-like clouds hanging at the bottom of a thunderstorm, it's a pretty good indication that severe weather is on the way. So these last few pictures of clouds will wrap up Chapter 4, and we'll begin to think about Chapter 5. Chapter 5 is all about atmospheric stability and cloud development, and why clouds develop, the reason why clouds develop with vertical extent, the reason why some clouds develop flat. It has to do with whether the atmosphere is unstable with lots of lift or stable with sinking air. And then once we begin to understand stability and instability, we'll see how clouds become precipitation, how cloud droplets become raindrops, possibly snowflakes, and then why we have different types of precipitation. Why does it rain one day and then perhaps snow in another area, and why does snow turn to sleet, or when is it freezing rain? Those will all be parts of what we'll take a look at with Chapter 5.